Okay. Welcome to the class, online lecture of week 5. In last week we discussed limits and how to compute limits of the different function. And today's main topic is derivative. It's quite relevant to the limit because derivative is basically a limit problem. And sometimes it is also called rate of change. As you heard, the derivative is simply rate of change. So I will try to explain what rate of change and how it can be seen as rate of change and how it is a limit problem. So you need to know the problem of finding tangent line at any point of the curve, or finding the velocity of an object moving along some curve. Both involve a limit problem, and indeed a same kind of limit problem. So such limit problem is called basically derivative. In other words, if I highlight this first topic, the first one, the finding tangent line to curve involves a problem of limit, right? So it is quite the tangent line is quite relevant with the derivative, the concept of the derivative. Initially, let's this point, then that, maybe this one, and it goes to. I mean, we're considering that Q is approaching to P and X is approaching to. So applying that limit in that formula, this limit, we will have slope of the tangent line at particular given point P. It means that the point Q is nothing but it's just a very close point to P, and this slope of that very tiny secant line is basically slope of the tangent line, right? So आप जितनी पॉइंट Q दूर लेंगे आपका secant उतना दूर होता जाएगा, लेकिन when Q is quite close to P, then basically you just zoom out P and Q. There is a small difference between P and Q, and tangent of that secant line is sorry, not tangent, but equation of that secant line is basically equation of your tangent line. So M is tangent, slope of tangent. Okay, so this is slope of tangent and it is equal to this one. So this was tangent formula, which basically introduced the concepts of the derivative, right? And this is the definition of the definition of the derivative. Okay. Now let's try the same notion in the with the help of an example. So now look, listen carefully. One point: derivative is basically slope of the tangent at particular point, right? So when in this question, notice that we are asked to find equation of the tangent line. Now slope of this tangent line is derivative. So in order to find tangent line, we simply, involve the derivative in this one. So this is point 1, m slope of the tangent is equal to this one, and simplification will give us the result, which is 2. 1 plus 1, 2. I hope you can understand these steps. And using this slope and given point 1, 1 and adopting point slope form of the equation of a straight line, we can have equation of tangent. Okay, and this is equation of tangent. So this was the example. We haven't started yet the idea of the concept, the core concept of the derivative. So we are building on the concept of the tangent. So now this red statement is quite interesting, and it's also important. We sometimes refer to the slope of the tangent line at a particular point on the curve, exactly the slope of the curve. Now slope of tangent line at that point is slope of the curve. Now slope of curve is kind of vague concept, because it's a curve which has different curvature, different movement, and it's difficult to measure the slope. But we imagine the analogy of small part of the curve as a tangent at that point. Now this can be explained with let's say this. Now this was the graph. This is point 1 1, 0 from 0 to 2 axis, and when we zoom it, I mean we zoom this point. Now for example, you want to know the slope of this curve. Now it's difficult to say what will be the slope of this curve. So basically that slope will be slope of tangent at this point, at this point. So you zoom it till let's say this point, like इसको इतना से zoom करेंगे, पहले 1.5 तक ये गया है, फिर 1.1 तक. Now again zoom this part, and you will feel like it is a straight line, and tangent to this part of the curve will be a straight line coinciding with this segment of the curve. So basically slope of tangent is the slope of the, okay, so this is what it is written. We zoom it and then find. Similarly, in this, where we started, the slope of the secant line P and Q is the slope of the tangent, right? So look, now this is point P where we want to find tangent. Now this is tangent, and okay, now this purple line is tangent. This line is a secant line. This is tangent. We kind of approximate tangent of this, the slope of this line as slope of this line, because it's not possible to find slope of this line. We only have one point, but for this line we have 2 points, and it is easy to find slope of this line. And once we find slope of this line, we say this is the same as this one, or these lines are same. So the bottom line is like slope of secant PQ approximates slope of T, tangent line, right, at point P, A and F of A. Okay? This is the concept. This is written as this one, the formal definition, and this is also called derivative. Now the same thing is explained in terms of velocity, because we started that two main problems like tangent and velocity, they involve some kind of limit, and that limit is basically same limit, and that limit problem is called derivative. So this is another example of velocity. We discussed with tangent. The same discussion will be with velocity, so I am skipping this for your self-perusal or self-study. And there is a follow-up example for velocity, example 3. I hope you will do that. And the next is derivative. From these two concepts, these two limit problems, we derive this derivative formula. Now this is called derivative of function f at particular point of a. There are different types of notations. Some people write like this, and some people write like d of a with respect to d of x at a, or people also write this d of f over d of x such that x is equal to a. Yeah, you may have seen other notations also. So it's just a matter of notation, and the core concept is set. Okay, so just a matter of notations, and Yeah. Now look at this exercise as example problem. X squared minus 8x plus 9. We have to find derivative at number a, or x is equal to a. So the definition is, we have already seen the formula. So derivative of f of a is equal to f of a plus h minus f of a divided by a plus h minus a, or effectively uh, f of a plus h minus f of a divided by h, and do not forget to put limit here. So limit h approaches to 0. Now this is definition of finding derivative, and this is how it's the same thing, definition, and using this function into this definition and a couple of simplification steps, we get this one again, taking h common, and so denominator h will disappear. Now 2a plus h minus 8, and applying limit h is equal to 0, we get 2a minus 8. Remember, the original function was x squared minus 8x plus some constant, let's say c, and this derivative of this function, as you know from your lower classes, is 2x squared minus 8 when x is equal to a. Now if you plug in x a instead of x, so 2a squared minus 8, this is the same stuff, right? So by classical definition, by the way you already used to do or compute differentiation or derivative, is basically coinciding, or they are same. Right? So I'll give it again. Now the main concept of derivative is what it explains geometrically or physically. Derivative is you already heard about this term, rate of change. So it gives you let's say the amount of change in dependent variable when you give some, or when you change your independent variable. So if you change your independent variable, you want to see how much your dependent variable changes, right? Everybody do that. In life you confront so many situations, like I do. I invest more time with let's say study or teaching, then I expect more output. Let's say if I invest more time in playing in the class with the students, talking other things apart from academics, then my expectations will be the why your output depending upon the number of hours or number of minutes talking about the subject. So it depends upon this thing. This is rate of change. So change in independent variable induces or causes change in dependent variable y. So this phenomena is called rate of change or derivative. And if you literally want to see if x changes from this point to this point, then change in x, also called increment or maybe addition, is denoted by this one, and corresponding change in y, it is denoted by this, and this is difference quotient, which ultimately defines your derivative when you put limit delta x is equal to 0, or the difference between these two approaching to 0. If difference between these two is 0, then this tells you the rate of change, the measurement of change in y when x changes. And this is concept of the rate of change of derivative. There are no more examples in this slide, in this presentation, part of the presentation. It's more like theoretical, and so maybe you must be feeling something like harder to understand it, but the next coming sections or coming presentations involve a lot of numerics. Here is some interesting example. So a manufacturer produces bolts of fabric with a fixed width like the cloth unity and with the fabric, the cost of producing X yard of this fabric is this one as a function of X, right? So the number of X, if you want to produce more yards, the cost will of course increase, right? So what is meaning of derivative of this? What are its units? So derivative means the change in X, rate of change of cost with respect to rate of change of yards. So this is derivative. And in practical terms, what this means to say the derivative at 1000 is equal to 9. What do you, I mean, how do you call this? There are three parts of this example, and the first one, derivative f, is the instantaneous rate of change of the cost with respect to x, that is differentiation f prime x means the rate of change of the production cost with respect to the number of yards produced. So this I already said you, the rate of change of cost with respect to the number of yards, and now yeah, it's because of this definition. Okay, and part B statement, this one, derivative at 1000 and the result is 9, means after 100 yards of the fabric produced, the rate at which production cost is increasing. Now this is not the production cost. Production cost was C is equal to f of x, and this is C prime or f prime. So this is the increasing in cost after producing this. It means this production cycle or production is an increasing, cost is a, let's say, increasing function. So you produce more yards, your cost is increasing per yard, right? So with respect to x means per yard, so $9 per yard cost is increased once you have produced 1000 yards. So you start from 0 here, the initial point is like 0. And alternatively, you can say when x is equal to 0 or 1000 yards are produced, C is increasing 9 times as fast as C, x. So in the start, for example, there was one cost, and after 1000 yards, the cost increases 9 times. So now this delta 1 is small compared to this one. We could use approximation delta C and say that the cost of manufacturing and if you, now this example is this change does not increase so rapidly. If you, let's say, incorporate delta x is equal to 1, it means you want to check the cost after 1001 yards, so it's not going to increase. It is still I mean at the rate 9, but if you want to know after 2000, then the rate might increase, right? The rate at which production cost is increasing per yard is probably lower when x is equal to 5, naturally, because it is increasing with x. Then when x is equal to 50, because of the economies of scale and manufacturer makes more efficient use of the fixed cost of the